today's class is going to be one of those where some people might want to watch it again. So that's why I'm starting the recorder. Alrighty. So today's lab is LD, ST, and LDI. So those are the three instructions that are mentioned in today's lab. So what I will do is I'm going to pick one of them and kind of show you how it gets the job done, and then you can kind of get the concept or at least an understanding of how how the processor works in that case. So of the three, I am going to pick LDI. Okay, LDI is the instruction that I'm going to demonstrate today. And if you anytime you have questions, and or you need more time to process, just let me know, okay? Because this is going to be one of those classes where, okay, you might need more time to process it. Hmm? Well, that's true for all of my classes, but this one is particularly dense. Hmm? Well, high density is how we can get all the points across, right? At the end of the semester, I can go like, yep, I covered all the material. All right, so this is the processor, okay, which is usually needed, but the most important part, the first part is the opcode table. So we're going to take a look at LDI itself and say, okay, how is it described? So LDI is row 19, which is right here, and we're going to take a closer look just so that it is easier to see. There we go. All right, so we'll start from column A and then go all the way to column D as usual. Column A is not complicated. Column A sets in the binary code of LDI or load immediate is 0110 as the most significant 4 bits, 11, okay, that's fixed also with only XX, which means it only needs one register, okay? You only have register X or the placeholder X to specify. Column B is a little bit interesting this time because we see LDI X comma I. Okay, we usually see Y, but not I. Okay, so what is I representing? I is an immediate, okay, an immediate value, which I think was explained up here too. I specifies a constant value that is determined at assemble time. Okay, not at runtime, but at assemble time. So the first question is, do we understand what is runtime versus assemble time? Runtime means we don't know exactly what the value is until we are running the program. Assemble time means when we assemble the program, we already know what that is supposed to be. Okay, so that's the difference between compile time, which is also assemble time in this class, versus runtime. Okay, so now we switch back to the description here and go like, okay, so these are the two different ways to describe it in RTL. So once again, what is RTL? RTL stands for Register Transfer Language. Okay, so this time the RTL is a little bit more complicated than before. So I am going to use the most accurate RTL to describe this. Okay, this is the most accurate way to describe it. So now is why you need this is why we need CISP 360. Okay, because in CISP 360, every single concept involved in this particular expression should have been explained. Okay, we start with PC++, which is not the same as plus plus PC. This is a post increment operator. So what that means is we're going to grab the value of PC, the program counter, which is a register, before we increment it, and then we do the dereference, okay? Because that's what the asterisk means is dereference. And then after this whole thing is done, then we increment the value of the program counter, okay? So that is the most accurate way to describe this operation. Then you guys go like, where's I? Why is I not a part of this? Because I is actually at the location the program counter should be pointing at. Okay, then you go like, but why? Who puts it over there? The assembler does. Okay, so we'll take a look at the code that is generated when we assemble LDI, an instruction of LDI, and then we'll see like, oh, okay, so that's why it takes 2 bytes for the LDI instructions as opposed to only 1 byte for add, subtract, and all the other ones. Okay, so the simplified version to look at this is simply to say the effect, not the mechanism, but the effect is this. So the effect is whatever I is as the operand is going to be loaded, or it's going to be copied to whatever X is representing. So I has to be a constant. 26 is a constant. Okay. um, you know, 5 times 10, the whole thing divided by 2 is also a constant. Okay, so I just has to be an expression that evaluates to a constant, and it can be done at assemble time, which essentially says it cannot refer to the value of a register because the value of a register changes at runtime. So we have no idea what the value is going to be when the program is running. So it cannot refer to the value of a register, but anything else is going to be okay. Um, all right. So we're going to go take a look at a particular instruction, and we're going to use the assembler to help us to take a look. So we go to the source tab, get rid of whatever we had before, and at this time we just go like LDI. Okay, let's use register C this time, and I will give it a really simple expression, which is a constant, no more than just a regular constant, but it is a special one. We'll use 42. And then we'll put a halt instruction right after, just as a good practice. This is how we do it. Okay. In fact, I'm going to change it a little bit. I'll put a no up here first because if I have enough time, I want to show you guys how to use River Spider, because it's really a great tool. But to do that, I need that no op to begin with. All right, so the first thing is when we are at this stage of this class of the semester, it's a good idea to go take a look at the assemble tab. In other words, it's like, okay, we know this is going to be 0, 0, okay, as a byte. We know this is going to be 0, 1 as a byte. We know something about this one. According to the opcode table, or the opcode table, it should assemble to a 6, and then this XX is trying to represent C, which is 1, 0, excuse me. So this would be 1110, which is an E. So it should assemble to 6E as an opcode. Okay, we know that too. But what we may not know at this point is what about the 42? Where is it going to be? That's going to be the byte right after the opcode. So 42 is decimal. So in hexadecimal, because when we look at RAM content, it is all in hexadecimal. So what is 42 in hexadecimal? Think in terms of how many 16s do we need and how many ones do we need to represent the value of 42? Well, I think we need 2 of the 16s to make up the 32, and then we need a 10, right? So we need 2 of the 16s and 10 of the ones. So the 2 of the 16 is just a 2. The 10 of the ones is going to be A, because digit A is representing what we know as this constant, this value. Okay, I'm waving my hand instead of pronouncing it, because if I pronounce it, people would think, oh, 10. No, no, 10 is how this quantity is represented in base 10. The same quantity is represented as digit A in hexadecimal, which is also 1010 in base 2, and so on. Are we doing okay so far? All right. And for people who are not currently in the class, I do apologize that you cannot see my hand gesture, but this is also more reason for you to show up. I don't know who's missing in class. I have no idea. Maybe the whole class is already here. All right, so we go to the assemble tab and see what is happening here. Okay, so we see the no op is at location 00, and the no op instruction is the content of 00. Okay, that's something we have established before. The halt instruction is at location 03, and the opcode is 01. Yeah, we established that too in the previous class. The LDI instruction is at location starting at location 01. There's the 6E. The 6E is the actual opcode. In other words, the processor will decode the 6E and then go to 6E0 in the ROM, and then whatever is at that ROM is going to establish all the multiplexers, demultiplexers, enable this, disable that in order for the operation to go through. And then once again, we have the 2A. Okay, the 2A is our 42. Okay, so this is how the immediate value is represented. Okay, the assembler is responsible to figure out what value it is and then just put it right next to the opcode. Are we good so far? The 6E is the actual opcode. The 2A is technically not part of the opcode. It is the byte containing the value that we want to put into, in this case, register C. Are we good with those concepts? We good? All right. So now we go to the RAM file, because the only way you can download the file to put it into RAM is to go to the RAM file tab. We go to File, Download, CSV. Okay, and we'll put it into, I'll just be ldi.csv. Okay, there we go. And then we switch back to LogicSim, go to the RAM component, and then we load image. And it's my temp folder called ldi.csv. And now we have the whole program here. Okay, the NOR instruction is not really particularly important, so we're going to quote unquote skip it. How do we skip it? 6 control, well, actually in this case, let me count. Fetch is the first control T, and then incrementing the microcode pointer is the second control T. Incrementing the program counter is the third control T. Decoding is the fourth control T. But the decode of an opcode of 00 will put us back to location 000 with the microcode pointer. So that means we only need 4 control T's in this case to execute a no-op instruction. Any instruction other than no-op will take at least 6, but the no-op instruction itself only takes 4. Okay, so so there are a few things I can imagine, that you're thinking about. One is I know exactly what Tech is talking about. I remember the whole discussion, or I understand the whole discussion of how no op as an instruction executes. I get everything. Great. Number two, I kind of vaguely remember how instructions execute. It's usually 6 if I remember correctly. Why is this one only 4? Well, okay, not too bad. Okay, you're still retaining most of the information. You just need to kind of think about the differentiation between no op and all the other instructions. Third option is I have no idea what Tech just talked about. That is a red flag to me. Okay, for those people, it is super important to review the material so that you understand that one single statement. Okay, so I'm trying to put in all these little checkpoints in my class, not only to tell you something, but also to tell you how you can evaluate whether you're understanding and absorbing the content of this class, because I don't want any surprises when we get to exam 2. Okay, yep, control T's. So each control T is changing the clock by 1 edge. So the first control T is a rising edge, the second control T is a falling edge, the next one is a rising edge again, and then the last one is again the falling edge. Okay, so this is also why I present to you the processor the way it is, because then you can repeat the experiment. freeze the whole thing in one particular step, look at the entire configuration, and then go like, why is it in this state? You can go through all the reasoning, look at all the components, look at the way the components are supposed to behave, and understand the whole thing. Okay, so I'm just gonna go through that process, okay, which is not fully explaining it. Okay, four control T's. One, two, three, four. Okay, so now what do we have? Okay, we'll take a look. We have the microcode pointer back to location 000. The clock is about to have a rising edge, so we are back to a fetch. Okay, so this time we are fetching the opcode of 6E. Okay, so now we are going to fetch and decode. So that will take three transitions. One, two, three. Now it is decoded. All right. So once it is decoded, oh, okay. We are ready to decode. We are not decoded yet. Okay, so we are ready to decode it because this is a falling edge. The microcode pointer is at location 001. So this is the decode stage. Okay, one more control T. And now it is at location 6E0 because the microcode pointer is at 6E0. So this is where we need to kind of go slow and take a look at the configuration of the entire processor. Okay. Can someone tell me again how many registers are outside of the register bank? We know the register bank has four registers, A, B, C, and D. So how many registers are outside of the register bank? Four. Mm-hmm. Flags. Yeah. Yep. So we have the microcode pointer, which is the one that we always look at first. And then we have the program counter. And then we have the flags register, which at this point we have not used yet. And then we have the instruction register, which is only useful in fetch and decode. After that, is not useful. So we have four additional registers. And then we have RAM, which is also something that is selectable that can do something. How long would it take you to go through all those five components and see which one is quote unquote in use? In other words, a bright green line is going into it. Yep, except for people who don't know where to find them, right? The flags register. Yeah, it's just called the flags register here. Okay, so all we have to do is look at those five things and say, okay, what is going on? Okay, I miscounted. There's a sixth component, which is the register bank. Okay, this is the register bank. It does have a bright green line going in. So we go like something about the register. Some register inside the register bank is changing. The program counter is going to change. RAM is doing something because it is selected. We don't know what it's going to do. We'll figure that out. And then the instruction register is not selected, so we don't have to worry about it. The microcode pointer only acts in the falling edge. This is a rising edge, so for now, we don't have to worry about it. Okay, cool. So we'll go look at all those clues one by one. Okay, it doesn't even matter which one you start first. I would start with something like this. Okay, I would start with the register bank. Okay, this line being green means what? What does it mean? Hmm? Well, it's a one. Okay, but what does RIEN means when it is a bright green? When it is a one, what does RIEN represent? What is RI? Register input. Okay, register input enable. When it is a one, it means one of the four registers inside the register bank is going to change. Okay, how do we know that? Because we talked about this already. This is the circuitry inside the register bank. When RIEN is a 1, the decoder is active. When the decoder is active, the implicit one into the decoder is going to be output to one and only one of the four outputs of the decoder, so that whatever it is going to has to be the enable of a register, which means register C in this case is enabled. The clock is going to be is going to have a rising edge, so register C is going to update. Are we good so far? So what would be the next question you're going to ask? We know register C is going to update. What is the natural question to ask after that? Exactly. So who is supplying the value to update register C? Does that make sense? Okay. So now we tracked it down. Okay. And which port of a register is used to specify the new content of the register on an update? Registered? Yes, exactly. Port D. So we follow that. You go like, oh, okay, that's easy. It's coming from register R reg in. So we go back to the main and go like, okay, it is going to this one to this Y over here. Now, if you ever have any question about which port goes to which pin on the outside, there's an easy way to find out. Okay, let me show you that. We have kind of talked about this already. You go to the appearance and then just go like, okay, click on this thing here, and it will show you in picture which input pin is corresponding to it. Okay, so this is the best way to figure out, okay, how is it connected to the main circuit. All right, so we know it's this one. It's coming out of the multiplexer here. This multiplexer is enabled because the enabled port has a 1. The select is specifying a dark green, which is a 0, which means now we're looking at this particular node. This is not a concern because this is an input. This is an output, but this the multiplexer is disabled, so we are not concerned about that. This is an output pin. Output pins actually only have an input port, so we're not concerned about that. This is also just an input port of the instruction register. It cannot specify content. And then we go all the way over here. It's like, it has to be you. Okay? So if this is something that is new to you, you need to write this down. Okay? And follow the steps at least a few times until you feel comfortable to know that, okay, I can track these things down. Okay. Now, if you say, but Tag, you're talking too fast, I cannot write everything down. Yeah, write down the time. Okay. It is about 10:53-ish when I started talking about this because, the whole thing is being recorded. Let me make sure. Yep, it is being recorded. There are times when I go look and go like, shit, it's not getting recorded. Okay, but this time it is getting recorded. All right, so it's coming out of this thing here. You go like, okay, so how do I read the activity of the RAM? We did a lab, okay, which is in the homework assignment form to you about how the RAM component works. Okay, so for people who try the infinite monkey approach when they do the lab and the homework, I am sorry because you did not learn what you're supposed to. Okay, but the process, that particular activity is supposed to help you understand how RAM works. The way it works is we first look at the select. Okay, it is a bright green, which means it is selected. RAM is saying like, I'm awake, tell me what to do. There are two things it can do determined by the load port here. If the load port is, I mean, it even tells you right there. Okay, if it is a 1, we are reading. If it is a 0, we are writing. So it is a 1 now. Okay, so we are reading from RAM. Okay, so what is the next question? We already know the D port of RAM is going to the D port of register C inside the register bank. We know we are reading. We know we are not clearing. We know that we are not resetting the content of RAM because otherwise we'll see everything being 0 here anyway. So what is the next natural question? What is remaining unknown about the RAM component at this point? Well, okay, so you're correct, but you jumped a few steps. Okay, you jumped a few steps. The question is, why am I looking at why am I looking at this location? Why am I looking at this? Okay, so what do we track down? How do we track this down? We track down the A port, right? The function of the A port is to specify, so which location do we want to do something with? Okay, that's the job of the A port. So you track down the A port. It is coming out of a multiplexer. This multiplexer has no enable, which means it is always enabled. The select is a bright green, which means we're selecting input 1 to become the output. So we track down the input, and then guess where it goes? The program counter. Okay. Now, the most important part about this portion of the discussion is this is why we used the asterisk here. Okay. When the whole concept of dereference was talked about in CISP 360, it is mysterious. Okay, the whole thing about what is the address of something and how do we dereference a pointer and so on and so forth, that's all mythical. Okay, they might as well use a unicorn instead of the dereference operator. Okay, but here in this class, the unicorn is mechanical. It is just a robot dressed like a unicorn, okay? Because now we know the exact mechanism of what does it mean to be dereferencing, okay? Dereferencing simply means an address is presented to the A port of memory, in this case RAM. That's all it means, okay? This is where I need, and the RAM goes like, understood, what do you want to do with it? In this case, we want to reference, okay? We just want to read from that location, okay? Do we have any questions about dereferencing? So is it helping? I mean, is this really kind of helping you to, yeah, go ahead. So you first and then you. Go ahead. It is reading from location 02 because, correct. Yep, go ahead. To the A port of RAM to be exact. You're trying to specify which location are we doing something with. Now, you can be reading, you can be writing, but nonetheless, it specifies which one of the 256 locations, in this case, are we interacting with. Go ahead. Mm-hmm. Mm, so the program counter is only connected to the A port of RAM, which means that's the only thing it can do is to specify which location are we addressing. Yep, right. Yep, correct. Correct. So the dereference is the action of using a value to specify what location we want to do something with. So that's dereference. But dereferencing can be on the right-hand side of an assignment, which means we are only reading, or it can be on the left-hand side of the assignment, which means we're changing it. Yep. All right. So, so the next question now is, yeah, I can see the program counter is 02, and I can see that location 02 is being addressed, and I can also see that 2A, which is our 42, is the output of the RAM, which is then being used in the register bank to update register C. Okay, so now the next question is, how do you think the program counter got to location 02? It is because each instruction execution cycle, even the execution cycle for no op, increments the program counter. Okay, that would be one, two, three. It will be the third control T or the second rising edge when we execute an instruction that increments the program counter. And we have done it twice. It started off as 00. So if you increment the program twice, the program counter twice, obviously it's going to be 02. So it is not by any accident that the program counter now has a content of 02, which is also now pointing at the immediate value, which is 42 in the program. Okay, all right. But there's one more thing. I like infomercials. But wait, there's more. Not only is register C in the register bank getting updated, you also get a bonus of update because the program counter is also enabled. It is also going to be updated. So as a bonus item for no additional cost to you, we are also going to investigate how the program counter is going to get updated. Is that okay? All right. So how do we figure that out? Well, once again, we look at port D because that's the input to a register. It's coming out of the multiplexer. The multiplexer has a select of 0, and that means we're looking at input 0 of the multiplexer, which is coming from, guess what? The incrementer. Okay, so the incrementer, or just an adder, is basically saying, okay, we are ready to update the program counter with 3 because it is 2. Okay, 2 plus 1 is 3. So now it would seem like we have a situation where we are pulling the rug from under ourselves. Because on one hand, we are using the program counter to point to RAM and go like, this is where we want because the program counter is 02. But at the same time, the program counter goes like, yeah, I'm going to update to 03 on the next rising edge. So are we having a problem or are we not having a problem? Well, since the design has been like this for a while, it means it is not a problem. So now the question is, why is it not a problem? Because if these changes are simultaneous, that means, we really don't know which location of RAM is outputting to register C's, D port. So what is going on here? Well, this is all thanks to the propagational delay. Okay, because of the propagational delay, it actually takes RAM a long time. Okay, in the real device, if you say, hey, go to this location, it takes a long time for RAM to go like, okay, give me some time. Let me do all the internal stuff. And then finally, the output of RAM is going to reflect the content of the location that you're addressing. So the order of that update is very significant. Okay. So when you buy RAM, okay, I'm sure some of you have bought RAM for your PCs and laptop computers. So when you buy RAM, it comes with all kinds of specification and whatnot. One of those specification is really just saying this, okay? It's a delay, what we call a wait state of how long does it take for RAM to update. It is in a order of at least 10 cycles. And 10 cycles of your RAM's your own clock speed, which is only measured in hundreds of megahertz. So that means, it takes a long time for RAM to do the addressing. So this instruction, the execution of this instruction in the real processor is not happening like right away. It would actually introduce the wait states so the RAM has enough time to actually do the addressing. So by the time we want to do this update here, okay, this particular update, that is almost instantaneous. This is according to the clock speed of your processor, which is in gigahertz. Okay, so you're looking at an update that will be done in a cycle, within a single cycle in gigahertz, as opposed to something that will update in multiple clocks, like at least 10 clocks, in the at a frequency of only hundreds of megahertz. So that means any update to the program counter will take a very long time to change what you're really addressing in RAM. That delay is so long that you don't have to worry about a single thing. Because the update of the program counter is instantaneous, this update is also instantaneous by comparison. So that means there's no problem. Okay, there is no problem. We are not pulling the rug from under ourselves because of the propagational delay. Yep, yep. It is definitely a physics thing because inside RAM, okay, it takes a long time to quote unquote. Okay, so do not confuse this term with the decode that we are talking about. So RAM needs time to decode the address port in order for the internal mechanism to really address the correct content at the location that you want. So that's a long time, and that's also why we have DDR type of memory and so on. But that's kind of a topic for another day. So the bottom line is we don't have an issue with pulling the rug from under ourselves, but we do have the effect. So this particular instruction has two effects. The first effect is register C will change to whatever we specify. This is in binary, so we can expect this to change to 0100, which is the 4. No, I take it back because it's supposed to be a 2A. So it would be 0010 for the 2, and then the A is 1010. That's what we're expecting register C to become. And then the program counter will increment to 11, which is 3. So I know it's a little bit harder to do it. You cannot monitor two things at the same time, but I would just go ahead and say that this will change to 0010, 1010. This will change to all zeros and then 1, 1. Okay, on the rising edge, which is what we're going to do now. So Control T. Okay, let's double check. 0010, 1010. Cool. And this is all zero except for the 1, 1 over here. So it updates two registers at the same time. Okay. When you look at the RTL, that is actually reflected in the RTL itself because the program counter is post incremented, but whatever the X is a placeholder of a register that is also updated. So that's why the RTL is important because it actually shows you the mechanism by which the instruction is implemented, as opposed to just the effect of the instruction. So now the question is, why do we have to increment the program counter? Because if we don't increment the program counter, then the next instruction execution cycle will be screwed up. Because, okay, let me go back to here. Because now we are ready for the next instruction execution cycle. And if we did not increment the program counter, then we would have executed 2A as an opcode, which is not what we want. Okay, we want the opcode that is next to the 2A because the 2A is really just a constant that we want to put into register C. We need to increment the program counter to be ready for the next fetch cycle. And that's exactly why the program counter itself also needs to be incremented. Yes. Yep. Hmm. That is correct because that's what the instruction specifies. That's exactly what LDI is supposed to do, loading a constant value into register. So I think you're asking about why this instruction is useful in the program. Hmm. X is 10 because 10 is C. Okay. Okay. Because this is the only way for you to specify a particular value and store it into a register. There's no other way to initialize a register with a specific value. You can, in a way, well, okay. So, short of doing something like this, there are other ways to do it. There's also an increment instruction. So, let's take a look at the other way to do things if you insist that you do not want to have the LDI instruction. So, we do have an increment instruction which increments the value of a certain register, but it is useless to you unless you already know the current register's value. Right. But there's a way to reset the value of a register with an instruction that we have already talked about. Subtract. You can subtract the register from itself and therefore turning it to 0. So You can achieve the same thing as LDI C5 with subtract CC and then 5 increment C instructions after that. The problem is when you have a more complex or higher value to initialize, then you just have a long string of increments, which may not be the best use of the 256 locations that we have in RAM. All right, so there's that. And now we're going to play with label definitions and generally speaking expressions. So the assembler is actually quite flexible in terms of what you can specify over here. You can actually use labels too. So we're going to go into the discussion of a label. Okay. So let's just say that we want to define the label L1 over here. And then after that, we use byte 24 over here. So I'll explain what these two lines are doing. And the best way to look at this is from the assemble view again. So the job of a label is a bookmark. Okay, it is just a bookmark with a alphanumeric name, so it's easier for you to refer to it. So in this case, L1 is associated with the address that is right after it. Okay, so 04 is the definition of L1 in this case. Okay, and byte 24 or 24 is really just telling the assembler and go like, I need to reserve a byte at right here at this location, which is 04, and I need the content of that byte to be exactly 24 in decimal, which is also 1/8 in hexadecimal. Is that okay so far? Are we okay with the definition of a label, which is the alphanumeric name followed by a colon? So the colon is important because without the colon, it is not the definition of a label. So you need a colon here. Are we good so far? So this is how we define a label for the location, and then this is how we specify the content at that location. Now, can I put a label anywhere in the program? Yeah, sure you can. Absolutely. So if you want to put a label here, you can put a label before no op, but then I have to move everything down a little bit, and that's going to screw up the spreadsheet, so I'm not going to do it. All right, so how do we know the definition of a label or how it is defined? Once again, the best way is to locate the definition of the label and then look at the address right after that, and go like, okay, this particular label L1 is defined as 04 in this program. Okay, but what does it mean that a label is defined as 4? It means every time you see the label L1, it is just 4 in value. Okay, all right, so let's go ahead and do something here. And let's go try to re-express 42 as something related to label L1. Mhm. At location 0, no, this is at location 04. No, byte 24 is the content at location 04. L1 is just an alias of 04. So L1 has no existence when the program is running. It is just a label so that when you are assembling the program, you can refer to it like this. Are we doing okay so far with that concept? Okay, so we'll just keep it like this for now, and then we go to the Assemble tab, and you can now see the constant that we're loading into register C is now 04 because label L1 is defined to be 04. But the content at location 04 is 1/8 because that is defined by byte 24. Does it have to be a byte definition? The answer is no. You can put any instruction here if you want. You can do a sub CC, and if you look at the Assemble tab, it is now 9A, which is the opcode corresponding to sub AA. So the content at the location 04 is not important. The label definition does not care what you put at that location. It just says every time you refer to L4, we are referring to the address of this location. We don't know what the content is. We don't care what the content is. We just know the location is also called label L1. Are we good so far? All right. So now I'm going to show you some flexibility of what kind of value can we use when a single value is expected. Okay. In other words, in the opcodes table, anytime you see an I as a part of the mnemonic definition, you can replace it with any expression. But the expression has to be in postfix format. So that means if you want L1 plus 16, okay, if this is what you really want, then you only can express it as this. Okay, so we know L1 is 4. 4 plus 16 should be 20. So let's double check whether it is actually 20. You go like, Tack, you're wrong. No, this is 1 4 in hexadecimal, which is 1 of 16 plus 4 of 1. And guess what? That really is 20. Okay, so this is called RPN, or reversed Polish notation, or postfix. Those are all referring to exactly the same thing. Okay, all right. So we are going to take a quick exercise, a little kind of side excursion to take a look at what is RPN. Okay, so we can look at RPN. RPN stands for several things. No, we're not dealing with that. Reverse Polish notation is the one that we are using. Okay, so there's a whole description of what it is, how to work with it. You can look it up. There are calculators, tools online that can help you do the conversion. Okay, so what it is normally the expression that we use on a daily basis is called infix notation. It is called the infix notation because to express 3 plus 4, the plus is between the operands or the values that you want to add. So from the perspective of the position of the operator, it is in because it is between. Okay, so that's why it's called the infix notation. This is what we are used to. But infix notation has a problem. Okay, so let me use my text editor to illustrate the problem, which to most people is a problem that is easily solved, but the solution is actually very not elegant. So where's my mouse pad? Where did it go? Mouse pad. It's not starting. Okay, try one more time. Mouse pad. There we go. Nope. All right. So let's take a look at um, 2 times 6. Okay, that's infix notation, meaning 2 times 6, which is 12. And then we'll take a look at 3 times 5, okay, which is 15. So what do I need to do to add the 12 to the 15? So we go like, oh, okay, we just need to do something like this. Okay. So when you look at something like this, how do you know that we are not supposed to multiply the 6 to the 2, add the 3 first, and then multiply the 5 to the sum? How? Hmm? The order of operations in C++ and all programming language, it is implied by the priority of operators. Okay, so in C++, we prioritize multiplication first. So that means without any additional parentheses, we know that, oh, okay, so it is implied that we have to perform the multiplication first, and then we add the two products to become the final outcome, right? Okay, so let me give you another example. So let's say we have 2 plus 3. Okay, you go like, that's easy, that's a 5. And then we have 4 plus 3, which is a 7. And I go like, okay, so how do I express the product between these two? They go like, okay, so it's 2 plus 3 times 4 plus 3. That's not going to work, right? Because your compiler is going to go like the 3 plus 4 is going to be done first. So we're adding the 2 to the 12, and then we add the 3 to the 14. So the whole thing is going to be 17, which is not what we want. So in this case, because of the priority of the operators are not defined in a favorable way, so now this time we go like, okay, we have to use parentheses. Does that make sense? Okay. So we're going to get rid of the unnecessary parts here. Okay, so we get rid of this, and then we get rid of this. So postfix, it means in order to specify an operation, you specify the value that you want to operate first, and then the operator is specified last, and therefore the name postfix, because it is after, right? Or RPN, which is reverse Polish notation. So in this case, how do we do this? You go like, okay, we specify the 2, we specify the 6, and then we specify what to do with those two. So now we have 12. You go like, okay, so what else are we going to do with the 12? Hold on, just let it sit, okay? And then we proceed to specify 3, 5, multiply. So now we have two values. The first value is the output of this. The second value is the output of this. Then you can specify what are we going to do with those two values? Add them together. What about the second one? Kind of the same thing. 2, 3 plus, 4, 3 plus, multiply. So that would basically calculate 2 plus 3 over here. It will then it will store it, and then it's going to calculate 4 plus 3. It will store the 7. So now we have 5, we have 7, and then we ask what are we going to do with the 5 and the 7? Multiply those two. So now it will give you 35. That's how RPN works. Okay. So why do we use RPN? Because parentheses is difficult to parse. Okay, in order to process parentheses, the parser, which is the part of a compiler or assembler, to go through the expression to figure out the structure, is complicated. Can it be done? Obviously, it can be done, but it takes resources. Okay, and I'm lazy, so I go like, well, we're just gonna use postfix notation because it is the easiest to parse. Is that okay? Yes. Now, in terms of the actual structure of the code or the expression, it doesn't really matter because the by the time you execute a code, by the time you get to the object code, like your program that you actually run on the PC, it doesn't matter either way because the compiler is the one that has to handle that complexity. But once the compiler is done, it doesn't matter whether you represent it as a prefix. The prefix notation is going to look like this. Okay, so if you want to look at the prefix notation, so prefix notation still needs parentheses because the prefix notation is going to look like this because you specify the operation first. And then whatever value you end up with, you then decide, so you specify the operation and then you specify the value that you need to operate on. So this is prefix, this is postfix, and this is infix. So those are the three different ways of expressing expressions. And all three are used in the literature of computer programming languages. This is the most common one because we have been poisoned since elementary school to only use infix notation. Okay? That's just tradition, okay? It's just a convention for no particular reason, okay? It's actually a really bad standard because how do you specify something that needs like three parameters? It's not easy, right? Because infix notation means the operator is between the things that you're operating on. So what if you have three things to operate on, like the ternary operator? Then you need to invent like, oh, okay, this is the symbol between the first and the second, and this is the one between the second and the third. Okay, It's not natural. But if you use postfix notation, not a problem. Specify the three things and then you specify the operation, good, no problem. Postfix notation and prefix notation, neither one has a problem with that. So postfix notation, the second, that's the one that we are talking about. And then prefix notation is basically how you call functions. So if you think about a function call, it really is more or less a prefix notation because you name the function that you're calling and then you use a comma separated list for all the parameters or the arguments. That's basically a prefix notation. Is that okay? So you know about prefix notation because you know how to perform function calls. You know the infix notation because that's what you have been learning for the past, one-ish to decades or so. So you ask who is crazy enough to use a postfix notation? Programmers, exactly. There are programming languages that makes use of the postfix notation. The first one is obvious by the name, but not so well known because of its visibility. It's called PostScript. Okay, so what does it tell you? Post means postfix. Script means it's some kind of a programming language. So you ask, who would use something like this? PostScript is a language. It's also usually abbreviated as PS. It is a language understood by printers. So think about when you want to print something, okay? You want to print some really kind of complicated floor plan of a building, okay? You want to send it to the printer. The printer has a super high resolution, 1200 dpi by 1200 pdi, which is kind of like not too super high precision by today's standard. So you go like, okay, so you got two options. You either figure out the entire bitmap before you send the bitmap over, or you send instructions so that the printer goes like, okay, so what do you want? Oh, you want to draw a square over here? Sure, I can draw a square over here. You want to draw a circle over here? Yep, I can draw a circle over here. So which one is a better way to do it? Sending over a bitmap or sending over instructions? They're less device dependent. Okay, the instruction is less device dependent because you can have a low resolution printer that's only capable of say 300 by 300 dpi. It doesn't matter because you're saying, okay, I need this square to start at 1 inch in this direction and 2 inches in this direction, and then draw a line from here to over here. You're only telling it the locations of the endpoints of a line or the parameters of a spline and stuff like that. So that is why we need a language so that the computer can tell your printer what to put on a piece of paper, right? But you can also think of your screen as a piece of paper. So the same language, PostScript, can also render things on your screen the same way that it will render on the piece of paper. So that's why PostScript is super duper useful back in those days. So you ask, so we are not, I take it that we are not using it anymore? No, it just gets a new fancy name these days, PDF. It just got a fancier name these days. It's called PDF, Portable Document Format. So I think I have sufficiently conveyed the actual usefulness of PostScript or postfix notation because it really is actually used. Most people do not think about PDF as a programming language, but it is. It is just a dressed up version of PostScript in the sense that you can have interactive elements, you can use a form, which I absolutely hate. Okay, you can have little check boxes that people can interact with. But other than that, when you're drawing things on a piece of paper, PDF is retaining everything that PostScript had. It just added stuff on top so that you can also interact with forums and other things in the PDF. All right. So if you don't know how to do the translation between the formats, there are tons of tools online that can help you with that. Okay. So Getting back to our little sample program here. And let's just say that we are obsessed with the value of, what was it before? 42. That's right. Okay. And we are obsessed with that value, but we only want to use L1 with the minimum number of additional constants. So what can we do here? L1 is 4, so we want 42. So let's see what we can do. There's no power, unfortunately. There's multiplication. So we can say, that times 10 and then 2 plus. Okay. So this is saying, okay, what is L1? It's 4. This is 10. What are we going to do with those two? Let's multiply. So this will give us 40. And then we go like, okay, this doesn't tell us what to do. Fine, it is just another value. So now we have 40 from here, and then the 2 over here as two different numbers. And then this specifies whatever number that you have, add those together. So now we have 40 plus 2, which is 42. We can double check to see if this really is 42 by looking at the Assemble tab alone. And we got our 2a back, which is not. It is 42 because it's 32 times plus 10, so it is 42. So we are all good. Yep. Sub CC. So sub CC, which is the 9a, is from assembling. It's from the opcode table. So you go to the sub instruction, the subtract instruction, which is where is it? Right here. So you have a 9 here because 1001 is a 9 in hexadecimal, right? And we specify C and C, over here. C is 10. So we have 1010, which is an A in hexadecimal. So that's why we have 9A. Is that in the assembler or not? Let me double check. It is 9A. Okay. Then you go like, wait, hold on a second here. We specify a 9A here because that's the opcode corresponding to sub CC. But if I hand assemble and determine that we have 9A over here, we should be able to replace the code with a byte instruction or the byte, we call it a directive, but it's kind of like we're just telling the assembler what to put at that location. So that means, oh, so if I specify a byte and say it is 16 times 9 plus A, which is a 10, then it should have the same effect when it comes to the content of the program. Okay, let's try to see whether that is the case or not. So you go to the Assemble tab, it's like, oh, we got our 9A back, but it looks completely different. Yep, it's just two different ways to specify, I want this byte to be a 9A. So how you specify the 9A, there are many ways to do it. Okay, you can specify an instruction where the opcode is actually 9A, or you can use the byte directive and go like, okay, I can hand assemble the whole thing, and this is 9A in a RPN format, the reversed Polish notation. All right, are we good so far? Okay. Now you can even compare labels or even do calculations between the labels. So if you look, oh, I can't do that. That's stupid of me. Don't do this. Okay, do not do that because it will ruin the assembler. So I had to undo it. Okay. So now, what do you think is L2 defined to? We know L1 is defined to be 0, 4. What about L2? What is it defined to? 0, 5. Okay, it is whatever is the next location. So L2 is defined to be 0, 5. Okay, and some of you may be thinking, I wish there's a way for me to really just take a glance and know how the labels are defined. Well, there's a way. It's not the best, most obvious way to do it, but if you scroll the tab all the way to the right-hand side, there's a tab called Sim tab, which is symbol table. Okay, that tab is table. So when you look at this, this is what we call JSON, JSON, which stands for JavaScript Object Notation, okay? Which is not terribly important in the context of this class. All you need to do is to say uh, L1, okay, these are all in lowercase. L1 is defined on line 3, and the RPN expression evaluates to 4. And then you go like, what about L2? L2 is defined on line 5, and the value is just 5. And neither contains any error messages, so both have 0 error, basically. Okay, so with these, now we can have even some additional form ability, because now you can define a label, let's say L3, and oh, I used the wrong tab again. Okay, to go back to the source tab. So now you can go back to the source tab and you now go like, okay, I want to define a new label. Let's call it L3. And I want it to be the sum of L1 and L2. And you can do that. Okay. One is 4, the other one is 5, right? So it should be 9. So you look at the assemble tab, it won't tell you anything about L3. It just goes like, yeah, we can assemble L3. It's not a syntax error. So in order to see what value it evaluates to, SymTab always tells you. So now we can see that L3 is defined on line 6. The RPN evaluation ends with a value of 9. That's it. All right. So the SymTab sheet is actually quite useful if you need to figure out what the values of the labels are. But typically, you do not need to know that other than just doing today's lab, because the whole point of using labels is so that you don't have to keep track. Alrighty. So do we have any questions about everything that we have talked about today? There are quite a few concepts involved. No particular questions? Okay, all right. So we can start the lab early if you guys want to, because I don't have anything to add at this point. We good? Okay, let's do that. All right, so the lab is LDI, LDST, and LDI. And let me change the time because I set it up to start at 11:50, so we can start a little bit early. Oh, I did not. Okay, so there's no start time, which means I can just, all I need to do is to unhide it. Then you guys can start to do it. Okay, give me a second. I have to get rid of this first. Cancel and make it visible, and I'll show you the access code is just LDI or lowercase, so nothing special about this one. All right, I am going to close or stop the recorder.